Hi, I'm Kritish, and this is a lightning presentation of our work Spam. Spam is a multi-threaded last-level cache covert channel. It achieves a high bandwidth by exploiting hardware prefetching. Let's start with some background on cache covert channels. This is the cache hierarchy in modern processors. L1 and L2 caches are private to each core, while the last-level cache is shared among different cores. This sharing of the LLC leads to covert communication. Let's say the sender and receiver are two processes running on different cores. They agree on an address beforehand, and to transmit a bit 0, the sender loads and installs the address on the cache. And when the receiver reloads it, it encounters a fast cache hit. On the other hand, to transmit a bit 1, the sender does nothing, and when the receiver loads it, it will be a slower cache miss. The receiver will time the load on its side and based on a threshold decode the bit. The transmission rate of the bits of a covert channel is of significance because it determines the potential of the corresponding side channel in terms of the leakage rate. So the motivation behind this work is to increase the maximum bit rate achieved by an LLC covert channel. The previous state of the art in terms of bandwidth for LLC covert channels was Streamline, which was proposed in 2021. In Streamline, a sender encodes each bit using a different address of a large shared array, and the receiver follows behind the sender in time, decoding each bit sequentially. When the LLC is filled, the next address, A of 6 in this case, will evict the first installed address A of 0 and reset the channel for further communication. However, the drawback of Streamline is that since it uses a large shared array for communication, there is a possibility to parallelize the encoding of bits or parallelize the decoding of bits. However, this does not happen in Streamline, which limits its bit rate. Hence, we extend Streamline with multiple sender thread and multiple receiver threads. So the setting here is as follows. The sender uses multiple threads running on different cores to parallelize encoding, and the same is done on the receiver side. Multiple threads running on different cores decode concurrently. So we expect such a channel to have a high bandwidth. However, the bandwidth is limited due to various factors. One of those key factors is co-running noise. Co-running noise could either be from cache activities of benign applications that co-run with the channel, or it could be from a defense such as noise injection. To illustrate the same, let's say that a bystander thread running on core 6 performs noise injection. So this will pollute the cache by loading random addresses and cause eviction of some of the addresses used by the channel. And because of this, when the receiver decodes this bit, it will encounter a cache miss and result in a false decoding. So the error rate increases because of this. And to avoid this, we have to keep the senders and receivers close to each other so that as soon as sender encodes a bit, the receiver can decode it. And in order to bound the sender receiver gap, we need frequent synchronizations, which will in turn result in a drop in the bitrate because during synchronization, the channel is idle without communicating. Spam proposes to solve this problem of bandwidth drop due to co-running noise. We argue that fewer but faster senders should encode for more receivers for achieving a bounded sender receiver gap. So Spam proposes an unequal distribution of threads between senders and receivers. For example, two senders encode for four receivers in this case. And in order to sustain such an unequal distribution, we need faster senders encoding for more receivers. So the challenge now becomes how do we accelerate the senders? And we do that by exploiting the property that encoding and decoding order need not be the same. For example, as long as bit 2 is encoded before it's decoded, bit 0 is encoded before it's decoded, bit 1 is encoded before it's decoded, it does not matter whether they were encoded in order. So by changing the encoding order, we in turn modify the access pattern of the sender, and access pattern of the sender is modified in such a way that some of the prefetches are triggered on the sender side, accelerating the sender. On the other hand, the receiver evades prefetches through its access pattern in order to accurately measure the load latency. By accelerating the senders, we can accommodate fewer senders for more receivers, which will in turn achieve a bounded sender receiver gap with fewer synchronizations and lead to a noise resilient channel. To know more about our work and see the results of bit rates and error rates achieved under different noise conditions, check out our paper available at this link, or you can also access it by scanning this QR. Thank you.